And welcome. This is the last regular season video. After that, we're going to overtime or playoff time for the review. So let's take a look at this. We're going to talk about exponential growth and decay. You should be exposed to some versions of what exponential growth and decay are, either in chemistry or in physics or something. Mainly we see it in cell division. Hey, we're going to have cell after cell keeps dividing in half, dividing, doubling, right? And we have exponential growth. You should be familiar with this type of graph as well as exponential decay. So in calculus, we explain exponential growth and exponential decay as something that is increasing or decreasing continuously at a rate that is proportional to the material that is there. So I'm looking to say something is increasing or decreasing at a rate, continuously at a rate. So my rate gets translated into dy dt, my change in my stuff over the change in time, proportional to the material that is there. Okay, proportional k to the material there that is y. Okay, so I have a differential equation. K is some constant. Okay, that's being used to find out how much of my material keeps getting reduced or increased, depending if it's growth or decay. Okay. So, well, what does that mean exactly? Well, if I were to have this and I were to solve it like a differential equation like we had in 6.1, okay, so if I have my differential equation, so what do? I separate my y's and my t's. So I'm going to divide both sides by y and multiply by dt. So I get 1 over y dy is equal to k dt. So I've separated it, and well, what do I do next? Well, my next step is to integrate. So I separate, now I integrate, and the derivative, what function gives me derivative of 1 over y? Well, it's the natural log of the absolute value of y is equal to kt plus c. Don't forget the c. Okay. Well, I'm going to solve for y in this case. Well, how do I solve for y? Well, you raise each side to the e. So e to the natural log of the absolute value of y is equal to e to the kt plus c. E raised to the natural log of anything. Is that anything? I can separate this to e to the kt times e to the c. Because these are exponents, and when I multiply exponents, okay, when I multiply something with the same base to the exponent, hey, that's going to get me my plus c is really a, adding up. That means I can separate and multiply by the same base. Okay. So, well, what can I do from here? Well, since I know e raised to anything times e raised to anything is always anything, this is going to be positive. This is going to be positive no matter what I do. So I don't need my absolute values there anymore. And so I end up with y is equal to e to the kt times, and this e to the c, well, it's just a bigger constant. So I'm going to make a really big c. And so I can rearrange this y equal to a really big c e to the kt. And that looks a lot like an exponential function. In fact, this is the exponential function that we're going to be dealing with when you talk about growth and decay. And this is one that you need to have memorized. Okay? If you don't have it memorized, you need to have this memorized and be able to do all this work. So what I want you to be able to do, okay, and what is C? Well, glad you asked. C is going to be our initial amount of material, e to the kt. This right here is initial amount. this formula is what you need to have memorized. Okay? If you do not memorize it, then you need to be able to memorize this and know how to work through this entire part all over again. My hint to you, memorize this. Okay? So here we go. Let's look at some examples. We have 3 examples. I'm going to go kind of quickly so I can save your time and value it. So this first example says the number of bacteria present when the experiment began was 1,200. That should get you a hint to this. This right here is my initial amount. Okay. After 100 hours, there were 2,700 bacteria present. Assume exponential growth and find the time required for the number of bacteria to increase to 30,000. So if I take a look at my equation, y is equal to a naught e to the kt, I have 2 unknowns, my initial amount and k. The people that make up problems will never, ever, ever give you k. Never, ever. It's always going to be up to you to find it. Great, you say. So you have to be able to use some of the other pieces of information. The other piece of information is I'm going to use this right here. After 100 hours, there are 2,700 bacteria. I need to be able to use that information in order to solve for k. So what I know is that my y is 2,700 is equal to my initial amount of 1,200 e to, I don't know what k is, but it happened over 100 hours. Okay? And so I begin the process of solving. I could divide both sides by 1,200, and what I end up getting is 9 over 4 is equal to e to the k times 100. Well, I need to solve for k, so how do I do that? I raise each one to the natural log. So I get the natural log of 9 over 4 is equal to 100k. And then I go ahead and I plug into here. And this is the natural log of 9 over 4 over 100 is equal to k. And now some of you are going to be really tempted to grab your calculator right away and put this in and find a decimal approximation. Wait. Don't do that now. Wait until the very end, okay, of your problem, and then do it at that point. Okay? We're not at the end yet. So then what do you do with this information? Well, now that I have a general equation, I know how much I started with, the 1,200. I know what k is now. And now I can answer the question that was being asked, which is find the time required for the number of bacteria to increase to 30,000. So now I set this other problem where I have 30,000 is my y. I still have 1,200 being my initial amount. E, I now know what k is, ln of 9 over 4 divided by 100 times some time I need to find out. So I go ahead and divide each of these by, again, divide both sides by 1,200. Okay. That's 300 over 12. Over 2, which is 25, is equal to e to the ln of 9 over 4 divided by 100 times time. Okay, again, raise each one to the power of, take the natural log of both sides so I can solve for t. So I get natural log of 25 is equal to the natural log of 9 over 4 divided by 100 times time. Or, and then I now have 100 natural log of 25 divided by natural log of 9 over 4 is equal to t. Now you get your calculator out. Okay? And when you get your calculator out, it will tell you that the answer is 396 0.936 hours. There's my time to get to 30,000 bacteria. And you have to ask yourself, does that make sense? Well, if I started 100 hours later and I get to more than double to 2,700, that means another 100 hours later I'm going to more than double 2,700, let's say, to 6,000. Okay, so I'm at 200 hours, I'm at 6,000. Okay, I'm going to go up to 300 hours, and I'm going to more than double again, so I'm going to go to like 15,000. And then I'm going to go to, well, another 100 hours, that's 4,000. I'm going to almost double again. Oh, it's 30,000. Yeah, that kind of quasi makes sense, okay? So it's, you got to kind of just see, does your answer make sense? You wouldn't want this to be like 7,000 hours. That wouldn't make sense, okay? Or you wouldn't want this to be 40 hours either. You got to put it in context of the problem and see if it makes sense. Okay. Next. So it says in a certain research experiment, okay, a population of fruit flies increases according to the law of exponential growth. So when you see this terminology here, you need to be thinking to yourself, oh, well, wait, that's A, not E to the KT. Okay. If there were 180 flies after the second day of the experiment and 300 flies after the fourth day of the experiment, how many flies were there in the original population? And here's what I'm going to tell you, is that if they give you two data points like this, that are where one of them is not the original amount, you need to do it this way, okay? So what I do is I set up a table. I set up a table of days, and I'm going to say number of flies. They tell me that on 2 days there were 180 flies. And on 4 days there were 300 flies. All right. But here's what's kind of cool about anything, about math in general, is that if you don't like the scale that's being done, push it back. Redraw it for a second. And I'm going to say, you know what? I'm going to call this new table over here my days. And I'm going to ignore what they said about days. And I'm going to say, you know what? The original day that I'm going to look at, day 0, my initial amount is going to be 180 flies. And you know what? 2 days later, it's now 300. Notice that these days, 2 to 4 and 0 to 2, are the same number of days. Okay? Except I'm reclassifying when this happens. Okay? So if I reclassify when this happens, and all of a sudden this equation, okay, I start off by getting my second data point of 300 is equal to my initial amount of 180 e to the k times time, which is 2 days. Again, when I'm doing this, I don't know what k is. I got to solve for it. Well, this is an interesting way to do it. I've never done anything like this before, you're saying. Well, this is just another neat trick that I'm pulling out of my Math Algebra Wonderfulness book and being able to say, hey, you can do this. This is kind of cool. Okay, I go ahead and divide by 180 on both sides. So that's going to be, let's see here, 5/3 is equal to e to the 2k. Take the natural log of both sides. I get natural log of 5/3 is equal to 2k. Natural log of 5/3 divided by 2 is equal to k. All right, great. So what did I do in the last one? Well, in the last one, well, I wanted to find out, well, I want to know some amount y that was happening. I know this is now 180, and I know I know k is going to be 5/3. I mean natural log of 5/3 all over 2 times sum of time, your days. Well, in our last example, we knew how many days, not knew many days, we knew what y was, and we had to find the days. Now they're telling us to go find out what my amount of flies were, but I need to know what days are. So, but they don't tell me that either. Okay. So again, we have to put things in relative order. I want to find out when the problem was at my initial number of days. Okay, so what was my initial or original population of the flies? But remember, I transferred all this over to my days, not just days, but my days. So this 0 represents what in my days? I'm hoping you're saying -2. Okay? Because I set up the scale for my days. It was the exact same number of days that passed, except I changed the scale on where things started. Perfectly legal for me to do. So now when I do this, my days I'm going to put in here is my days of -2. Okay, so now I just simply go through the process of solving. Okay, 180 e to the natural log of -5/3. Okay, and for just so you know, this negative on the outside now becomes an exponent. Okay, so this is really equal to 180 e to the natural log of 5/3 to the -1. Well, e to the natural log of anything is just that anything, so this is equal to 180 of 5/3 to the -1 power, which is the same thing as saying times a 3/5. And so that's what y is equal to. And so y is equal to 108 flies. So what does that mean? That means when my days was at -2, I had 108 flies. But my days of -2 is what the days were, the original days were 0, and my initial amount of 108 flies. Kind of cool. Okay, it's kind of heady. Get used to it. All right, it's like boom. All right, so here we go. Last problem. Here we go. Last example. It says here, let y represent the mass of a particular radioactive element whose half-life is 25 years. How much of a 1 gram mass would remain after 15 years? Again, half-life, just so you know, is that if you begin with a gram of an element, only half a gram would remain after 25 years. 1/4 of a gram would remain after 50 years. It just poof, disappears. Okay? So how do I set this up? Whew. Again, I don't know what k is. All right? I know that y is equal to a sub o e to the kt. Did they tell me what my initial amount was? Sure, it's 1. Now with these half-life problems, they may not always tell you what the initial amount is. But guess what? You can always pretend it's 1. Always pretend it's 1. And if I have 1 for my initial amount, e to the kt, well, what's the time that it took for it to reach a half? Well, you told me that took 2 years, not 25 years. So I take the natural log of both sides. Natural log of 1/2, okay, is equal to 25k. Natural log of 1/2 divided by 25 is equal to k. And there's my k. Notice it wasn't something nice and easy. You still need to go through and solve for it. Okay. And then I need to go find out, well, how much mass remain after 15 years? Okay. Well, when I do this, my initial amount is equal to 1. E. K is now natural log of 1/2 over 25 times 15. All right. Now we're kind of at a point to, this is going to require a calculator. And when we put this in our calculator tells us that y is equal to 0.659, in this case, grams. Also, just as a future reference, okay, that if you get to a problem that asks you what percentage of my unknown mass of radioactive equipment remains after 15 years, well, again, when you're pretending that might have 1 gram, and I find out that I want it to be half as much later, this is okay. And guess what my percentage, no matter what my initial amount was, my initial amount will only 65.9% of it will be left over, no matter what my initial amount was. So if my initial amount was 100 grams, I would have 65.9 grams left over. Does that make sense? Okay. All right. There are your examples. Here's your homework. It was a grand experiment. I'm hoping that this worked for you, and I look forward to doing the review with you. We'll see you guys later. Bye.